Now let's take a look at implicit differentiation, which is section 2.5 in your textbook. So really the first thing we need to do is talk about what is an implicitly defined function and what is an explicitly defined function. Once we know that, then we can talk about how we can use implicit differentiation to find the derivative of, obviously, an implicit function. So everything that we've done so far has been in explicit form, which means y, or f of x, was all by itself. There was nothing crazy where y was being multiplied by x or y and x were being added and whatever. This is explicitly defined because I can write it as y equals or f of x equals. However, some functions are not written that way. For instance, what if I have the function y equal or x times y equals 1? Well, now I don't have just y by itself. I have the function defined implicitly by the equation xy equals 1. To find the derivative for the equation, I have to be able to write it explicitly, which sometimes is super duper easy, like this example. If I have xy equals 1, it's really easy for me to obviously manipulate this to take it divided by x on each side to get y equals 1 over x, or y equals x to the negative 1, which as we know is the same thing. Then to find the derivative of that function, then I'm going to use this guy, obviously x to the negative 1, and say the derivative, y prime, would be negative 1 x to the negative 2, and then rewrite it in that form. So again, just because it's explicit doesn't mean that it's impossible. This was a very easy example, but let's take a look at some that are not quite as easy, where we can't solve for y necessarily as a function of x. So if we can't, then we have to differentiate implicitly with respect to x. So this is where things are going to be a little bit more difficult. For instance, let's look at this function. Can I do anything to get the function to be y equals something? No, I sure cannot. So in order to differentiate that function, I would have to use implicit differentiation. So it's kind of like what we've been doing with the chain rule, when essentially if I'm differentiating a term involving x alone, I would differentiate as usual. So like this guy in my derivative equation would be 2x, just like normal. This guy would still be 0, just like normal. However, if I'm differentiating something with y, then I'm going to have to think about it in terms of y prime, like the chain rule. So what if I were taking the derivative of negative 2y cubed? Well, that would be negative 6y squared, using the power rule, but then times y prime, because I'm not differentiating with respect to y, I'm differentiating with respect to x, so I have to include that y prime. Same thing would go here for y. The derivative of that would just be 4, but I also have to take it times y prime because y, again, we're differentiating with respect to x. Let's take a look at a couple of examples before we move on to actually working through full examples together. So just to kind of show you the difference, this first guy is written explicitly. Explicitly because I have d over dx, which means I'm deriving with respect to x, and I'm taking the derivative of something that only includes the x as a variable. So doing that derivative, super duper easy. I already know how to use the power rule that says take that 3, move it out front. That's where that 3 comes from. And then x to the second power. I'm decreasing 3 by 1. So that's really easy. That was an explicitly defined function. Notice here, if I'm taking dx, which is the derivative with respect to x of y to the third, then I'm going to use the power rule, or chain rule, really, the general power rule, that says take the 3, move it out front, take y to 1 power less than, but then also take the derivative of y. So here they're using dy over dx. Typically, the way you'll see me write it is like this, because y prime is the exact same thing as this, and I don't have to write as much, and I'm very lazy. So this is how I would write that one. For my last one, notice I've got a variable that agrees and a variable that does not. So again, the variable that agrees with what I'm differentiating with respect to is an easy derivative. The derivative of x is 1. The derivative of 3y is 3, and then the derivative of y. So again, I would write this as 1 plus 3 y prime is how I would differentiate that.